All right, we're about to dive deep inside the atom to get to know a single tiny particle that dictates almost everything. I mean, from the color of a firework to the chemistry of life itself. We're talking about the electron, and well, it plays by a very, very strange set of rules. So let's start with a puzzle that completely baffled early scientists. You know, opposites attract. So what in the world keeps these negative electrons from just spiraling into the positive nucleus? Why doesn't every atom in the universe just collapse on itself? And for that matter, what's stopping them from just flying off into space? It feels like it should be one or the other, right?
Well, to solve this mystery, we've got to understand where electrons are, what they're doing, and the bizarre quantum rules they're forced to play by. And believe me, this isn't just some abstract theory. These rules are basically the operating system for our entire physical world.
Okay, let's get into it. First, we have to talk about how our thinking has evolved. You see, the early models of the atom were really simple, neat and tidy, but they were also just plain wrong. They couldn't explain the electron's weird behavior, which meant we needed a whole new way of looking at things.
So we basically threw out that tidy solar system model with electrons circling like little planets. Instead, we have the modern view, the electron cloud. And here's the crucial takeaway. An electron isn't a tiny dot on a map. It's more like a fuzzy cloud of probability. We can never know exactly where it is, only the region where it's most likely to be at any given moment.
Now this brings us to one of the most fundamental rules of the quantum world, quantized energy. The best way to picture it is a staircase. An electron can be on step 1, or it can be on step 2, but it can never, ever hang out in between the steps. Energy isn't a smooth, continuous ramp. It comes in these specific, bite-sized packets.
And this whole staircase idea, it explains so much. When an atom absorbs the exact right amount of energy, one of its electrons gets excited and instantly jumps up to a higher step. But it can't stay up there. When it falls back down, it has to release that extra energy. And it does so as a little particle of light, a photon. That's what creates the unique colors we see in everything from neon signs to fireworks. Right, so if electrons live in these specific energy steps inside a probability cloud, how do we actually describe where one is? Well, to do that, scientists came up with a kind of quantum address. This address tells us everything we need to know. First, you've got the principal energy level. We call it N. Think of this as the floor in a skyscraper. The higher the floor, the more energy it has. Then, on each floor, you have sublevels, which describe the general shape of the room. And finally, orbitals, which tell you that room's specific orientation in space. And here's how it all fits together. As you go up to higher energy levels, higher floors in our skyscraper, you get more types of rooms or sublevels available. That's why each level can hold way more electrons than the one below it. The building basically gets wider as it gets taller. Okay, so we've got all these available spots. How do atoms actually fill them up? Well, it is definitely not random. Nature is incredibly orderly, and atoms follow a very specific logical set of rules to build what we call an electron configuration. And the rules are actually pretty simple. First, you always fill from the lowest energy level up. You start on the ground floor. Second, each individual orbital can hold a maximum of 2 electrons. That's it. And third, there's a kind of politeness rule. If you have a bunch of orbitals with the same energy, each one gets a single electron before any of them get a second one. No crowding.
The best way to really get these rules is to just use them. So let's build the electron configuration for an atom we all rely on every second. Oxygen. It's got 8 electrons we need to find homes for. Okay, here we go. Following the rules, the first 2 electrons go into the lowest energy spot available, which is the 1s orbital. So we write that as 1s2. That's 2 down, 6 to go.
Simple enough. The next lowest level is the 2s orbital. So we put 2 more electrons there. That brings our total to 4. Now we have just 4 electrons left to place. And finally, those last 4 electrons go into the next available spots, the 2p sublevel. Now the p sublevel can hold up to 6, but we only have 4 left, so we write 2p4. And there you have it, 1s squared, 2s squared, 2p4. That's the complete quantum address for all 8 electrons in an oxygen atom. So why on earth did we just map all of that out? It's not just a bookkeeping exercise, I promise. It's because everything that matters in chemistry, everything, happens in one place, the outermost shell. The electrons living out there are the ones that run the entire show. These outer shell electrons have a special name. They're called valence electrons. They are the MVPs of chemistry. They're the ones that determine how an atom behaves, what it bonds with, and pretty much all of its properties. For our oxygen atom, we just look at the highest energy level, which is level 2. It's got 2 electrons in the 2s and 4 in the 2p, giving it a grand total of 6 valence electrons.
And now we can take this knowledge of electron shells and use it to explain a real-world property, a pattern you can see right on the periodic table, the actual size of the atoms themselves.
So when we talk about atomic size, what we're really measuring is pretty straightforward. It's just the distance from the center of the nucleus all the way out to those all-important valence electrons on the edge.
And here is the big payoff, where all these rules meet reality. As you move down a column on the periodic table, atoms get bigger. And that makes perfect sense, right? Each step down, you're adding a whole new energy level, a new floor on our skyscraper. So of course the atom's edge gets farther away. But, and this is the really cool counterintuitive part, as you move across a row, atoms actually get smaller. How can that be? Well, even though you're adding electrons, you're also adding more positive protons to the nucleus. That stronger positive charge pulls harder on the same outer shell, sucking everything in just a little bit tighter.
This just shows you how incredibly powerful that electrons' address really is. It solves the puzzle of why atoms are stable, it dictates their physical size, and it controls literally all of their chemical behavior. The location of this one tiny, fuzzy particle defines the properties of everything around us. So it kind of makes you wonder, what else about our world is secretly being governed by the beautiful and totally bizarre code of the electron?